Oh, not that. So I don't know if y'all noticed, I was going through and updating everybody's grades. So I added points back to all the exams, and I've now been getting in the homework assignments. So hopefully you guys can see that happening, and you'll be pleased with the grades, hopefully. I want to see if this is the one that I had updated. Oh, well, shoot, let's see. Oh my gosh, there's too much stuff here. Hold on, I'm gonna minimize. Well, let's go this route, because I know I sat there and I named it different. So I'm gonna have to put this one up on Blackboard for you guys. I added a few things in here just to help go over, well, definitely the independent sample t-test, the formula for that. And I added in here this little graph that shows more or less what I was explaining or trying to draw for the effect size. Okay, so remember, effect size essentially is showing us the overlap or the lack of overlap, right? We have a lot of overlap here. We don't have too much overlap in these two distributions, and that's why we would have a large effect. Okay, so whatever this is over here, oh, they're saying it's height of men and women. We can see that on average, men truly are taller than on average women. Okay, of course, there are women that are taller than some men, and there are some men who are shorter than some women. But for the most part, you can see a distinction between those two distributions. This one, I'm not sure if you all remember, I kept saying about the verbal scores of men and women. You hear this a lot out on the street whenever they're talking about verbal scores, that women score higher than men on verbal fluency and things like that, when actually, despite there being a significant difference, and so it is okay for them to say that, the effect is really minimum, right? And you can see this here. So this distribution on this side, this would be women over here, and this would be men over here. So there is a difference between the means of these two distributions, but it's so slight. Okay, there's a lot of overlap. So this is why we say, yeah, sure, women do score higher on verbal skills, but it's really not that much of a difference. Okay. All right. So the last week, we started talking about the two ways that we can measure or I don't know, let's see, I guess, construct a design of a study where you have two different groups. Okay, we did this before where we only had one sample and we compared it to a population. Now we're going to be looking at two different samples, and so ultimately there's two ways to do the two samples. We have the paired samples t-test, and then we have the independent samples t-test. Okay, the paired samples t-test, we went over this, that there are three ways. I hate that that's saying that it's unstable. There are three ways to make your pairs or to make your groups. Okay, so I won't go over all the examples of these because we did this the last time, but we have the natural pairs, we have the matched pairs, and then we have what we call repeated measures. And this is where each individual goes through both levels or both treatments of the experiment, okay? Oftentimes we call this a pre-test, post-test scenario. And yeah, okay. So I had showed you all then the formula for a paired samples t-test. And I mentioned that I really wanted you guys to hang on to this D, okay, D. We're going to have to calculate D in order for us to get our T, right? So we're going to ultimately have to find this D score. And what that is a difference score, okay, a difference score. So let's look at this real quick. So here's a little graph, and this is saying a subject. We don't call them subjects anymore. That sounds kind of sinister. We would call them like a participant or a volunteer, right? When you call them a subject, it's like you're doing evil things to them or something. So anyway, so these are the people, okay, person number 1, person number 2, and so on. And we have now an X1 and an X2 because we have 2 samples, right? Now this one is not telling me what these numbers are. So I don't know. We could make up whatever we want. It really doesn't matter, okay? But this individual, the first time around, had a score of 122, and the second time around had a score of 111. Okay, I'm working on losing weight, so let's think of it as weight, although I don't think someone that weighs 122 needs to lose pounds, but you know, whatever. Okay, so this person that weighs 131 here at time 1 now weighs 116. Okay, somebody who weighs 127 now weighing 113. This would not be good data. This is, don't even go with that. But anyways, 123 to 119. And then individual number 5 originally scored 132, and then it went down to a 121. Okay. So how we get D is we just subtract. Okay. 122 minus 111. Why does it have it as negative? That doesn't even make sense. I did not make up this this chart. I don't know if I'd be able to do something that fancy. This came from his stuff. Oh, wait, go. Let's see real quick. That is so weird. Right? Can anyone see? Do you guys agree with me that that's really strange? That would, right? I mean, I'm not going crazy, right? That would not be negative. These are the only things that only supplies that I get from, or resources that I get from this author are his tables, which is kind of nice because it's a pain in the butt to make tables, but this one is really strange. Okay, we're getting a single sample. Unless I did pull that with me from somewhere else. That is so weird. Oh no, that's already ANOVA. There's oh, I didn't use his because it was so long. There were so many examples. It's like we don't need that many people in a study. And then here's a paired sample, but it didn't run the data. Okay, so I don't see that. So that must have been my bad. I got that from somewhere. But as I'm looking at it now, I don't that doesn't even make sense. But I mean, ultimately, it's not going to matter, which is the nice thing. But please know, I recognize that this would not be negative, okay? These would all be positive, and therefore you would get a positive 55. So that's frustrating, okay? But I'm just going to write it. I mean, it's not, you'll see it's not going to matter, but is equal to 55. So we're going to take off all those negatives, okay? And ultimately, when you square them, it doesn't matter either, okay? You get the same number. The only time that the positive and negatives in D is going to matter is if they're if you have some negatives and some positives, right? And you're trying to add up D, that's the only time that that's going to matter. If they're all negative or if they're all positive, it won't matter. But yeah, so let's just go with positive 55 on there. If you square 11, you get 121. If you square 15, right, you get 225, and so on. Okay. Okay. So let's go back and show you how this would fit in here. So it's exactly like we would have done with the single sample t-test, okay? Just D is the new X. So in our example here, we would have the bigger number here, which I don't even want to make it up because I already forgot. Let's see, what was it? 679. 679, my computer's moving, minus, and then that 55 would go up here, okay? And it's going to square, and we're going to divide it by our n, and then it's all going to be over n minus 1, okay? So exactly what we were doing with the single sample t-test. Why I say that if it was negative 55, it won't matter, because of this right here. If it was negative 55, that's okay. We could put negative 55 right here. And when we square it, that would disappear anyways, that negative, okay? So that's why I was trying to tell you that it's okay, it doesn't matter. And I'm going to show you an example where if you have positive and negatives, that's where you have to pay attention to the negatives, okay? But in this instance, since they were all negative, it didn't matter. Okay, so you would square 55 here, right? Let's see. I don't have my phone with me, so let's get up our calculator here. Okay, so 55 squared, we get 3,025. I'm going to take this off here. I need a new slide. Oops. Okay, let me do this and get this one. It has that line on it, but that's okay. All right, so $679 minus, and then we'd have 3,025 right there, divided by 5, all over 5 minus 1. So then 3,025 divided by 5, we're doing it, we get 605. I'll go ahead and do the 4 right there. So 679 minus 605 should be 674, but I don't know, I never trust myself, so. Oops. All divided by 4, 74 divided by 4, we get 18.5, and then the square root of that, 4.3. So our estimated standard deviation for this example, oops, is 4.30. Hopefully you can see that okay. So exactly the same thing that we were doing before. The only difference is you have to calculate that D, that difference score. And you do that by just taking the first score and subtracting the second score, okay? Now, of course, we would do our, it says S of, how you would read this is the standard error of a difference. Okay, so the standard error of a difference. It's the same way that we calculate standard error in the single sample t-test. Okay, so our standard error of a difference, oops, that didn't look good. It would be 4.3 divided by 5, right? Or the square root of 5. Square root of 5 is 2.23. We'll round it up to 2.24. And so 4.3 divided by 2.24 equals 1.92. Okay. And then we'd have what we need for to calculate the t. But we didn't do something, right? We are missing the mean of the first. You can think of it as a group, but that might be a little bit confusing because technically this is the same person, right? The same person went through time 1 compared to time 2, okay? So you could think of it as the mean for the first group or the mean for the first level, the first time around, whatever you want to say, okay? So we need to get an average for this one, and we need to get an average for this one, okay? So let's do that real quick. Let's see, 122 plus 131 plus 127 and 123 and 132 equals 635 divided by 5. And so I get a mean for group 1 as 127, okay? Right, the sum of x1 equaled 635. And the n, I mean, you could say for group 1, but you don't have to because it's the same number of individuals, okay? It's the same person. So let's do group 2 now, or time 2, if you want to think of it that way. So the sum of x for the second time around, let's figure that out. So we have 111 plus 116 plus 113 and 119 and 121. So we get 580 for the sum of our time 2, that way. Obviously it's the same number there. So now the mean of our second group is 116, okay? So now, right, if you look here at the t, we have our mean of the first group, mean of the second group, or time 1 or time 2, and we're going to divide it by that standard error of a difference, which we have. So t is equal to, see if I can kind of see it, 127 minus 116 all over that 192. I don't want to try and guess that. 11 is 127 minus 116 divided by 192. And so let's see, let's go with that. 11 divided by 1. It's going to be a big score right here. 5.73. That's a really big T. But we'll check it out and see. We haven't done the critical values or anything like that. I'll show you guys all that right now. Okay, it's nothing different. It's the same thing. Okay, so we have our T-score. Okay, going back, let's see, and looking at this, we have no idea what this data was, right? We don't know what was happening. I was saying losing weight, but I would be really worried that people that weigh this much are losing weight. So I'm not worried, or I don't want to do that example. But anyways, so we would have to find the critical value, right? So we could see if our T-score is significant. Was there a significant difference between this group here and this group over here? Okay, having a big T like that, 5.73, pretty hopeful that we do. We are going to meet that, but let's just make sure. Okay, so I know I'm kind of going out of order here. I haven't done, step 1 with the hypotheses. I haven't done critical values or anything like that. And the reason why I didn't do that is I just wanted to show you how to work the formula. Okay, but since we got to a number, we might as well try and figure something out. So our N is 5. Okay, even though we have 5 X's in this group and we have 5 X's in this group, it's still, it's 5 people that did this study. Okay, so degrees of freedom would be exactly as we remember, N minus 1. So our degrees of freedom is 4. Okay, I'm going to go up here to this little chart. And again, we don't know, no one told us what to do. So we're just going to look at a two-tailed 0.05. Okay, and so the critical value there would be 2.776. Okay. And our T-value was 5.73, so it was really big, okay? Why I was saying that when I saw the 5, that it was, it's so big. Unless you're way up here, right, and you have a very small sample, you're only working with 2 or 3 people, and you have a T that's over 5, you are pretty much going to find a significant result. Most of our critical values are in the 2s. Some can be in the 1s and so on. But only if you have a really small sample do you need to kind of worry about big numbers, whether it's going to meet it or not. A T of 5 is going to be significant, usually in our examples. Okay. Let me see, are there any questions right now or over any of this part, this stuff? No, Cassandra, you seem you're okay with it? Okay, so should we do another example of this one, or go ahead and move on to the independent samples?
Move on.
Move on? Yeah, okay, yes, good, okay. And tomorrow I'll do more examples and we'll just, we'll look at that one. But I agree with you, Cassandra, it's pretty simple just because it's the same thing that we've been doing, right? The only difference, again, like I said, I'm gonna say it again, is you have to calculate D. Okay, you have to calculate D. Okay, so now a little bit into the independent samples. I'm going to minimize this just a little bit so we can read this. I believe we already went over this. This is a design type or a type of design that you purposefully have two different people, okay, or not two different people, you have two different groups. And the point is to measure, you know, how is group one going to do compared to group two? So these are not the same people. As if we saw right now in this example where it was someone doing time one and then time two. These are separate people, separate groups of individuals, as you could see with men versus women, right? Kids versus adults. Someone, you know, tasting Coke compared to people that are drinking Pepsi. I don't know, right? Separate people, separate groups, independent of each other. And so with that, with the separateness, we get a big formula, okay? Now, this first one up here, if you notice, it's if the ends are not equal. So say I had 10 men show up and I only had 8 women show up. Okay, I could still run the experiment and I could still run the statistics and see how that goes. Okay, that's for this whole formula is for if our ends are not equal. Okay, I'm going to save you the heartache right now. Our examples are not like this. Okay, so you don't have to stress about this one. Okay, we don't have to do this one. Although it's not, you know, that different than what we're going to be doing down here, other than the, you know, we weight it compared to how many people are in one group versus the other. I mean, you have a little bit of a difference of the denominator down here, but that's okay. Okay, so we are going to be working with this down here, okay? I don't really like that this is listed like this because it scares you. It makes you think that you have to do all of this. Really, what we're doing is we're just going to be doing this part right here. Okay, this is how we will be finding our numbers. Okay. This is if you already had the estimated standard deviation for the first group and the estimated standard deviation for the second group. Okay, we won't have that. We're going to work with our raw data. Okay, so we have this formula right here, and I know he's big, and I know he could be kind of ugly, and we might be scared of him, but it's really let's see, maybe it's tedious, but it's not hard. Okay, I promise you. So if you notice this right here, right, this little section here, we've already done that. That's what we do, right? That's the formula essentially for standard deviation as we know it, right? So what we're going to be doing is we have to calculate it for the first group, say the men, and then we're going to have to do it for the second group, the women. Okay. And then we'll do this down here, which this will be easy. Okay. So are you ready to give it a whirl? Give it a try? Hopefully so. It's going to happen whether you're ready or not. Okay. All right. I'm going to give myself another, hold on real quick. Find up one. There we go. Okay. So move him real quick. Okay, so let's look at this here. All right. This one is kind of nice. And I like this because it already gives us our sum of x and our mean. Okay, so we don't have to do all of this work right now. It's given to us. Okay, this example is from social loafing. If you guys have taken intro psych, I think we kind of talk about social loafing maybe in the social psych section of intro. If you've taken social psychology, then you probably have studied the idea of social loafing. And the idea is that when we are alone, we work a lot harder compared to when we are in a group. Okay, and you can see this in classic examples in school when there's group work, right? You always have the one slacker. When you're driving by all the construction in El Paso, it seems like there's only one guy that's working and everybody else is just standing around. So we know that people, when they work alone, they work harder. We see this out in the real world all the time. The cool thing about social psychology is we try and recreate natural phenomenon that happens out in the real world, and we try and recreate it in the laboratory or in a very clinical setting. And when you can do that, then you're giving more like credence or more power behind the idea that this is truly human behavior. Okay, we see it out in the real world and we can create it in the laboratory. When researchers find some, phenomenon or human behavior in the laboratory, we then try and go out and see if we can find it out in the real world. Okay, especially with social psychology, it's something that we try and do. So this example is they had like a tug-of-war rope on the wall, and it was hooked up to a machine that could measure pounds of pressure. So it could measure how hard you're pulling on that rope. Okay, so the alone group came in and they knew they were alone, and they sat on this stool or this bench or whatever, and they pulled on that rope to see how hard they could pull. Okay, now the next group of people was an interesting one because they were tricked. That happens a lot in social psychology experiments. They were tricked to believe that they were working in a group, and that would be kind of hard because they're sitting together and they're pulling on this rope, right? So what they do is they bring in, say, 5 individuals, and one person is this person, right? Only one person is being measured. Everybody else is in on the study. Okay, so they're just faking, they're just acting. They all sit down. It always works out that one individual gets chosen to be the first person. And so he sits down right in front of the machine to pull the rope, and then everybody else sits behind him, and they all pick up the rope. So he knows that they're holding it, but they're not going to be pulling on it. Okay, so they might kind of move it around so he thinks that they're also pulling, and he's the only one that's pulling. Okay, and these are the scores for those individuals who believe,